The world was on fire, and the flames were spreading faster than anyone could contain them. On December 7, 1941, the Imperial Japanese Navy launched its devastating surprise attack on Pearl Harbor, plunging the United States into a global conflict for which it was profoundly unprepared. The burning battleships and shattered aircraft were only the most visible symbols of the catastrophe. In the days and weeks that followed, as the nation scrambled to mobilize, a far more insidious and pervasive problem began to reveal itself, one that had nothing to do with naval strategy or air superiority, and everything to do with the basic, fundamental need for shelter. Across the vast expanse of the Pacific Theater, from the dense jungles of the Philippines to the barren coral atolls of Wake Island, American forces were attempting to dig in and hold the line. They were sleeping under canvas in standard-issue Army tents that were proving utterly incapable of withstanding the environment. Tropical downpours, which could dump inches of rain in a matter of hours, didn't just soak these tents. They caused the canvas to rot and disintegrate, often within a mere 3 weeks of deployment. The War Department's morning briefings, already grim with news of military setbacks, took on a new layer of desperation as field reports flooded in. They described entire supply depots submerged under floodwaters, critical ammunition stocks ruined by moisture, and most alarmingly, soldiers being hospitalized with pneumonia and other respiratory ailments because their shelter had literally fallen apart around them during a monsoon. The traditional solution, wooden barracks, was a logistical fantasy. Building them required skilled carpenters, a resource as precious and scarce as any war material. It required weeks of construction time on site, time that the advancing Japanese forces would not grant. Most damningly, it required lumber, a commodity that simply did not exist on remote sun-scorched islands composed of little more than sand and coral. The Navy, tasked with projecting American power across thousands of miles of ocean, did the math and arrived at a chilling conclusion. Using conventional methods, it would take them 18 months to build the necessary housing for the forces they needed to deploy immediately. The war would be lost in 18 months. In a war room in Washington, D.C., the scale of the crisis was laid bare on a large table covered in weather maps and construction timelines. Brigadier General Eugene Raybould stood over it, his face a mask of grim concentration. His engineers had presented him with an impossible equation. They needed structures that could be mass-produced in factories in Pennsylvania, shipped 10,000 miles across submarine-infested waters, assembled by exhausted Marines who may have never held a wrench, and then survive everything the Pacific Theater could throw at them. The list of environmental adversaries was exhaustive. 130-degree heat in the sun, Category 5 typhoons with winds that could shred steel, monsoons that dumped 15 inches of rain in 6 hours, and the ever-present lethal possibility of Japanese bombing runs. The existing options were all failures. The standard Army tent cost $12 but was essentially a disposable item, lasting 1 month in jungle conditions. A wooden barracks building cost $8,000 and required a skilled construction crew for 6 weeks. Neither option worked when you were island hopping across the Pacific and needed shelter for 50,000 men yesterday. The British, who had been fighting longer, offered a potential clue. Since 1916, they had been using a structure known as the Nissen Hut, a semicircular steel shelter invented by Canadian engineer Peter Nissen during the First World War. These corrugated iron half-cylinders could house 30 soldiers, required no skilled labor to erect, and had proven remarkably resilient in the sandstorms of North Africa. But the Nissen design carried critical flaws for Pacific deployment. The British version used heavy steel panels that required specialized lifting equipment, which was never available on a forward base. The ventilation system, adequate for the dry heat of the Libyan desert, would turn the interior into a suffocating steam cooker in the oppressive humidity of the Philippines. Most damagingly, each hut required custom foundation work, which meant pouring concrete or building wooden platforms, which immediately brought you back to the original carpenter and logistics problem. Raybould's team calculated they needed shelter for 2 million personnel across hundreds of islands and bases. The math was brutal. At conventional construction rates, the war would be over before half the troops had roofs over their heads. The human cost of this failure was already being written in letters home from the front. Soldiers described waking up with their boots full of rainwater, watching fungus bloom on their uniforms overnight, and the terrifying chaos of temporary tents collapsing during a storm, sending men scrambling in the mud at 3 a.m. The medical corps filed sobering reports that in some sectors, respiratory infections were hospitalizing more men than enemy action. This was not merely about comfort. It was about maintaining a fighting force that didn't rot away into ineffectiveness before it ever saw combat. The call for a solution went out to American engineering firms, university research departments, and the Navy's own construction battalions. The specifications sounded like something from a science fiction novel. Design a building that weighed less than a Jeep, could fit on a single railroad car, required no foundation, could be assembled in one day by men with basic tools, cost less than $1,000, and could survive conditions that destroyed permanent buildings. And as an afterthought that made the challenge truly ludicrous, have 10,000 units ready to ship in 6 months. It was February 1942, and somewhere in Rhode Island, a team of engineers was about to be handed this architectural impossibility and tasked with turning it into reality. The Quonset Hut blueprint arrived at the Navy's Bureau of Yards and Docks as part of a peculiar twist of wartime cooperation. British engineers, grateful for the flood of American supplies under the Lend-Lease program, shared detailed technical drawings of their World War I shelter design. It was a 16-foot wide semicircular tunnel made from corrugated iron sheets, bolted to an internal wooden frame. The officer tasked with evaluating it, Commander John Philip Drosfeld, studied the specifications and immediately saw both its genius and its profound problems. The genius was in the arch shape itself, a form that naturally deflected wind and shed water without complex engineering. The problems, however, were a laundry list that would doom the design in Pacific conditions. The British huts weighed 3 tons when disassembled, a shipping nightmare. They required foundation bolts drilled into concrete, defeating the purpose of rapid deployment. Their internal wooden frame would be a feast for termites and rot in tropical climates. Drosfeld circled the ventilation specifications with red ink. 2 small windows designed for Scottish weather would turn these structures into ovens at Guadalcanal's 98-degree average temperature. But there was another, distinctly American voice in this conversation, one that came from an unexpected corner. Buckminster Fuller, a visionary and often dismissed eccentric, had been preaching the gospel of prefabricated housing since the 1920s. His Dymaxion house concept, a factory-built, lightweight, centrally serviced structure assembled on site, read like prophecy in 1942. While the military hadn't directly consulted Fuller, his published papers circulated through engineering departments, and his core insight proved invaluable. Treat buildings like manufactured products, not traditional construction projects. This philosophy of mass-producing housing like automobiles, using industrial materials instead of traditional lumber, and designing for rapid deployment suddenly sounded less like the ravings of a crank and more like the only possible path to victory. The Navy consolidated this thinking at their facility in Quonset Point, Rhode Island. The location was strategic. Rhode Island had deep manufacturing expertise in sheet metal, drawn from its thriving jewelry and silverware industries. It also had proximity to the steel mills of Pennsylvania and shipyards that understood the demands of marine-grade corrosion resistance. In March of 1942, the Navy assembled an unusual and brilliant team. It included structural engineers from the Strand Steel Corporation, who had experience with prefabricated farm buildings, architects from the George A. Fuller Construction Company, who specialized in rapid assembly methods, and crucially, Navy officers who had actually served in the Pacific and knew what typhoon-proof really meant, as opposed to what it meant on paper. The team was led by Otto Brandenberger, and it was his farm building experience that turned out to be the key to unlocking the problem. His Strand steel barns used self-supporting arched panels that required no internal frame. This was a radical idea. It meant no wood for termites to eat and no complex joinery to fail during a storm. Brandenberger's proposal was simple but revolutionary. Eliminate the Quonset Hut's wooden skeleton entirely and make the corrugated steel skin carry all the structural loads. This violated conventional architectural wisdom of 1942, where steel was for bridges and skyscrapers, not for self-supporting buildings. But Brandenberger knew his barns had survived Midwest tornadoes without internal framing, and he was willing to bet the same principle could be scaled up to housemen. The British, through their painful experience in Burma and Singapore, contributed another crucial piece of the puzzle. Their Nissen huts in those theaters had taught them exactly how tropical environments destroy man-made structures. Fungus wasn't just a cosmetic issue. It ate through wood preservatives and paint within months. Humidity didn't just make things damp. It corroded metal fasteners until roofs collapsed. Insects weren't merely annoying. Carpenter ants could reduce wooden support beams to hollow shells in a single season. The British reports read like horror stories, but they provided the Quonset team with a definitive checklist of everything that had to be engineered out of the design from the very beginning. No wood in contact with the ground. All steel had to be hot-dip galvanized, not merely painted. Ventilation had to be aggressive enough to prevent lethal condensation. And every single fastener had to be accessible for replacement without disassembling the entire structure. By April 1942, the hybrid vision had crystallized. They would take the Nissen hut's brilliant arch geometry, strip out everything that made it heavy or vulnerable, add Fuller's mass production philosophy and American steel manufacturing muscle, and then engineer every single detail for the specific hell of Pacific Island warfare. The stage was set for one of the most intense and productive design sprints in engineering history. On April 15, 1942, Otto Brandenberger walked into a vast warehouse at Quonset Point with 30 of the best engineers he could assemble, and a deadline that would have been laughable if the war situation weren't so dire. They had 60 days to design, prototype, test, and approve a completely new building system that did not yet exist. The team moved into the warehouse working in shifts around the clock, sleeping on cots pushed against the walls, subsisting on Navy mess hall coffee, and the kind of intense pressure that forges either brilliance or complete collapse. Brandenberger organized his crew into specialist teams. One group focused exclusively on aerodynamics and structural loading, calculating how the arch would handle hurricane-force winds. Another team worked on the fiendishly difficult problem of how to nest the components for maximum shipping efficiency. A third group dedicated themselves to solving the joint and fastener problems that had plagued the British design. The first radical decision was made on day 3. They abandoned traditional architectural drawing methods, which could take weeks, and instead adopted a build and test approach. They would sketch a detail in the morning, have the metalworking shop fabricate it by afternoon, test it overnight under simulated storm conditions, and revise the design by dawn. This iterative, rapid prototyping approach is standard practice in the 21st century. But it was revolutionary in 1942, when buildings were completely designed on paper before a single piece of material was cut. The warehouse floor became a chaotic laboratory, littered with failed joint experiments, bent test panels, and increasingly refined versions of each component. The engineers borrowed a technique from aircraft manufacturing. Every part was assigned a number. Every revision was meticulously documented, and nothing moved to the next prototype generation without solving the previous version's failure points. The dimensions of the hut were dictated by brutal practicality, not aesthetics. It would be 16 feet wide, the maximum width that could fit on a standard railroad car without special permits. Each section would be 20 feet long, short enough that 4 men could lift a panel, but long enough to create usable interior space. The total length when assembled would be 48 feet, providing enough space to house 36 men with bunks, or to be converted into office space, medical stations, or supply storage. The Quonset team discovered that this size hit a sweet spot in structural engineering. Any smaller, and they wasted shipping capacity. Any larger, and the panels became too heavy for field assembly, or the arch would require internal supports, reintroducing all the problems they were trying to eliminate. The calculation of the arch's radius consumed 2 full weeks of their precious 60-day schedule. An arch that was too flat would allow wind forces to peel the structure open like a sardine can. An arch that was too steep would waste interior headroom and create difficult geometry for the end walls. Brandenberger's team finally settled on an 8-foot radius, creating a perfect semicircle that provided 7 feet of headroom at the sides and formed what structural engineers call a self-bracing arch. The corrugated steel naturally wanted to hold this curve, which meant the panels could be thinner and lighter than flat sheets would need to be for the same strength. Their load calculations showed this design could theoretically handle snow loads up to 40 pounds per square foot, and wind speeds exceeding 100 miles per hour. But theoretical calculations and the reality of Pacific typhoons were two very different things. By day 40, They had a prototype that looked like it might work, a Frankenstein's monster of riveted panels, experimental joints, and borrowed hardware. The first complete prototype was erected on May 25, 1942, by a crew of 6 sailors who had been given only 4 hours of instruction in basic hand tools. The assembly time was 14 hours. This was encouraging but not yet good enough. The Navy demanded single-day construction because marine landing schedules didn't allow for multi-day building projects. The team quickly identified the bottleneck, the floor system. They had been trying to include a wooden floor as part of the package, but it was the slowest part to assemble, and the first thing to rot in tropical conditions. The solution they arrived at was elegant in its simplicity. Eliminate the floor entirely from the basic design. The hut would sit directly on whatever surface existed: coral, sand, dirt, or, if they were lucky, gravel. For applications that required finished floors, those could be added later as a separate project. This single decision cut the assembly time down to 8 hours and reduced the shipping weight by 1,200 pounds per unit. On June 10, 1942, the final prototype stood complete. It consisted of 96 corrugated steel panels, each weighing less than 50 pounds, that bolted together to create 720 square feet of enclosed space. The total materials cost was $1,394. The total weight was 9,000 pounds. Now came the real test, an engineering interrogation designed to prove its mettle. Navy structural engineers descended on the prototype with wind load tables, typhoon data from across the Pacific, and a healthy dose of skepticism that this corrugated steel tunnel could survive what nature could unleash. The numbers they were working with were not theoretical. They were pulled from actual weather events. Typhoon Gloria had hit Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180. The 1935 Labor Day hurricane that killed 400 people in the Florida Keys had produced winds so powerful they sandblasted, paint off buildings, and drove wooden planks through palm trees like spears. If Quonset huts failed in a storm, the result wouldn't be mere property damage. It would be dead servicemen and destroyed equipment. Brandenburger's team started with the fundamental physics of the arch. When wind hits a flat wall, it pushes directly against the surface with maximum force, but a curved surface deflects the wind upward and around it, dramatically reducing that pressure. It was the difference between water slamming into a dam wall and flowing smoothly around a river stone. The semicircular Quonset profile meant hurricane-force winds would slide over the structure, rather than trying to punch through it. The corrugations added a second layer of brilliance. Those ridges, running lengthwise, created structural rigidity in the same way that folding a piece of paper makes it stronger than leaving it flat. Each corrugation acted like a miniature I-beam, resisting bending forces that would crumple smooth sheet metal. The mathematics of load distribution was fascinating. In a conventional rectangular building, the roof pushes down on the walls push down on the foundations, and everything depends on those vertical load paths staying intact. Storm winds can literally lift roofs off because the elements are separate. The Quonset arch changed this completely. It was a single continuous curve where every panel shared the load with its neighbors, a principle engineers call a compression ring, the same concept that has kept ancient stone bridges standing for centuries without mortar. The hoop stress, the tension trying to spread the arch apart at its base, was resolved by the ground itself. Each Quonset panel was bolted to the adjacent panel with 3/4-inch steel bolts spaced every 6 inches, creating what was essentially a 48-foot-long steel cable wrapped in an arch shape. But theoretical strength meant nothing without empirical validation. The Navy set up brutal tests at their facility in Davisville, Rhode Island. They built a full-scale Quonset and instrumented it with strain gauges, pressure sensors, and deflection meters. Then they waited for a storm. On March 3, 1943, a nor'easter hit with 75-mile-per-hour winds and heavy wet snow. Perfect test conditions. The instruments recorded the structure flexing by less than 2 inches at its crown, before returning to its original shape when the wind subsided. The panel joints held. Nothing leaked. It was a thrilling and slightly terrifying success. It meant they were about to bet thousands of lives on this design. Testing for the tropical environment proved more challenging. You cannot simulate years of jungle conditions in a Rhode Island warehouse. The Navy shipped a test unit to the Panama Canal Zone, where humidity averaged 85% year-round and temperatures never dipped below 80 degrees. 6 months later, the report came back. There was minimal corrosion on the galvanized panels and no structural degradation, but there was a serious problem with interior condensation. When the hot, humid air hit the relatively cooler steel at night, water literally rained from the ceiling inside the hut. The solution required adding ventilation louvers at both ends and along the ridgeline, openings that would let hot air escape and create airflow without compromising structural strength or weather protection. These vents added $47 to the unit cost but transformed the hut from a steel sauna into a space humans could actually occupy in tropical heat. The final engineering challenge was the foundation. How do you anchor a 9,000-pound building to loose sand or solid coral without pouring concrete? The answer was borrowed from tent technology and scaled up. Long steel stakes driven into the ground, connected to the hut's base with adjustable tension cables. For harder surfaces, the team designed a bolt pattern that allowed the hut to mount directly to wooden sleepers or pierced steel planking. The beauty of this system was its forgiveness. The structure could flex slightly with ground movement without tearing itself apart. In June of 1942, the War Production Board officially approved Quonset Hut manufacturing. What happened next was a breathtaking display of American industrial capacity, operating at its absolute peak. The Navy contracted with 10 major steel fabricators across the Midwest and Northeast, companies that 6 months earlier had been making grain silos and water tanks and were now retooled for military shelter production. The Strand Steel Corporation converted its entire plant outside Philadelphia to exclusive Quonset production. George A. Fuller Construction took over a former automobile parts plant in Chicago. Great Lakes Steel dedicated 2 rolling mills to nothing but corrugated panel production. By August, these factories were collectively producing 1,500 complete huts per week, and the numbers kept climbing. The manufacturing process was a masterpiece of assembly line logic. Massive 4-foot-wide steel coils arrived by rail, each containing enough material for 30 panels. Rolling machines corrugated the flat steel, creating the structural ridges at a precise 2 2/3 inches on center. This corrugating process itself work-hardened the steel, making it stronger than the flat sheet that went in. Next, the panels were dipped into molten zinc at 850 degrees Fahrenheit in a galvanizing tank. This wasn't a paint. It was a metallurgical bond where the zinc would sacrifice itself to corrosion before the underlying steel could rust. In the salt-laden air of the Pacific, this step meant the difference between a 5-year lifespan and a 50-year one. It cost an extra $112 per hut, but proved non-negotiable after field reports showed ungalvanized steel corroding through in just 8 months. The packaging of each complete hut kit was an exercise in obsessive logistics. The 96 corrugated panels were nested inside each other like stacked bowls, reducing the package height from 8 feet to a mere 14 inches. The end walls, plywood sheets with pre-cut door and window openings, were packed flat between the steel panels. All the fasteners, bolts, and hardware were boxed in a single wooden crate that included illustrated assembly instructions designed for men who might not read English fluently. The entire kit loaded onto one standard 40-foot flatbed railroad car. This packaging density was crucial. Every train heading to West Coast ports was a precious artery carrying Quonset huts, ammunition, food, or vehicles. There was zero room for inefficient cargo. The shipping choreography was a monumental feat. Trains left Philadelphia and Chicago daily, arriving at the ports of San Francisco, San Diego, and Seattle, where Liberty ships and specialized cargo vessels waited at the docks. Longshoremen loaded complete huts into ship holds using the same crane systems designed for tanks and artillery. A single Liberty ship could carry 200 Quonset huts plus their assembly hardware, shelter for 7,200 men. The War Shipping Administration tracked every cargo manifest because these weren't just buildings. They were strategic assets. A hut that shipped to Guadalcanal in September might house a bomber crew by October, making the difference between operational aircraft and pilots sleeping in mud. The assembly process on the receiving end was where the Quonset design genius truly shone. The Navy's construction battalions, the famous Seabees, developed standardized procedures that turned shelter erection into a choreographed ballet. A 6-man crew, 8 hours, 1 complete hut ready for occupation. The process began with site prep. level the ground, remove vegetation, lay down a gravel base if available. 2 men would handle the end walls while the other 4 wrestled the steel panels into place. The panels overlapped by 6 inches and bolted together with the 3/4-inch fasteners. No welding, no concrete, no skilled trades, just wrenches, a level, and men following the illustrated instructions. The speed record was set on Espiritu Santo in January 1943, when a specially trained CB crew erected a complete hut in 4 hours and 17 minutes. But that was showboating. The real achievement was the sustained production across hundreds of islands, where crews threw up 5 or 6 huts per day, day after day, building entire bases faster than the Japanese could bomb them. By December 1943, monthly production hit 8,000 units. The logistics network moved so efficiently that huts ordered in Pennsylvania could reach New Guinea within 40 days, including the ocean crossing. The cost accounting told the story of victory. Each Quonset hut provided 36 men with weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks: $12,000 in materials, 400 man-hours of skilled carpentry, and 6 weeks of construction time. The Quonset delivered shelter at 1/10 the cost and 1/20 the time. By mid-1944, the U.S. military had deployed over 160,000 units to every combat theater, housing capacity for nearly 6 million personnel, built in less than 2 years. The proof, as always, was in the brutal reality of the front lines. On Guadalcanal in August 1942, the first combat-deployed Quonset huts arrived on a beach where the temperature hovered at 95 degrees with 90% humidity, and Japanese bombers made daily visits. Marine engineers unloaded the flat-packed steel panels under sporadic artillery fire and started bolting them together in a coconut grove still scarred by the previous week's shelling. Within 12 hours, Henderson Field had 10 new structures housing maintenance crews for the battered F-4F Wildcats. The real test came 3 days later when a Japanese bomb scored a near miss. A 500-pound bomb detonated 40 yards from a hut full of aviation mechanics. The blast wave flattened surrounding palm trees and shredded canvas tents, but the Quonset flexed. Dirt and shrapnel rattled off the corrugated steel, and when the smoke cleared, the structure stood intact, with every man inside shaken but alive. The jungle itself proved as hostile as the enemy. Within 2 weeks, red rust streaked any ungalvanized fasteners. The salt air ate through standard hardware like acid. Fungus grew on every surface that held moisture, painting the interior with abstract patterns of black and green mold. The ventilation louvers that seemed adequate in Rhode Island barely moved the suffocating air. Marines began propping doors open around the clock and cutting additional vent holes with tin snips, violating the structural specifications but making the huts livable. These field modifications were documented and sent back to Quonset Point, where engineers incorporated them into later production runs. More ventilation, larger louvers, and every single fastener, no matter how small, galvanized. Iwo Jima in February 1945 presented a different kind of hell. Black volcanic sand that infiltrated every crevice, no topsoil for grounding stakes, and constant artillery fire from Mount Suribachi. Seabees arrived on D-Day +2 and started assembling Quonsets under fire, literally bolting panels together while mortar rounds impacted 200 yards away. The volcanic sand made traditional stake anchoring impossible, so crews improvised, filling empty oil drums with sand and cabling them to the hut bases. When a Pacific typhoon hit in March with 110-mile-per-hour winds, these improvised anchors held while wooden structures across the island disintegrated. The base commander's report to Pearl Harbor was succinct. Quonset Hut survived. Everything else gone. The Arctic environment tested the design from the opposite extreme. In Alaska's Aleutian Islands campaign, Quonsets deployed at Dutch Harbor and Adak faced temperatures plunging to -40 and winds regularly exceeding 100 miles per hour. The cold made the steel brittle, and early units suffered from panels cracking at the bolt holes. Engineers responded by specifying cold-rolled steel with different metallurgy for Arctic deployments and adding rubber gaskets at every joint to maintain flexibility. Heating the huts created new problems. Warm air meeting frozen steel produced condensation that reigned inside until crews learned to install insulation blankets and run ventilation even in sub-zero weather. By the winter of 1943, weatherized Quonset models included internal insulation, double wall construction for extreme cold, and modified ventilation systems. In the European theater, the huts demonstrated a different kind of resilience. At Palermo, Sicily, a Quonset pressed into service as an ammunition depot took a direct hit from a German 80mm artillery shell. The shell penetrated the steel skin and detonated inside among crates of small arms ammunition. The resulting explosion should have vaporized the structure. Instead, the arched shape channeled the blast force outward through the walls and roof in a pattern that left the structural frame twisted but standing. Explosive ordnance disposal crews noted that a rectangular building would have collapsed completely, trapping anyone nearby under tons of rubble. The arch's inherent strength meant that even catastrophic damage did not trigger total structural failure. The Pacific typhoon season of 1944 delivered the ultimate stress test. Super Typhoon Cobra hit the Philippines in December, with winds measured at 140 miles per hour and a 20-foot storm surge. At Tacloban, the storm destroyed 80% of all structures on the base. Wooden buildings exploded into splinters. Concrete block structures collapsed when wind undermined their foundations. But of the 43 Quonset huts on the base, 39 survived intact, and the other 4 suffered reparable damage, bent panels and torn seams, but no total failures. Engineers analyzing the survivors found that proper anchoring mattered more than any other factor. Huts with adequate ground attachment rode out the storm. Those with improvised or insufficient anchoring rolled away like tumbleweeds. By war's end, field performance data from 50 combat zones fed back into a process of continuous design improvement. The 1945 production models bore little resemblance to the 1942 prototypes. They featured better ventilation, stronger fasteners, improved insulation options, and dozens of field-tested modifications that turned a good design into an exceptional one. The Quonset hut had not just survived the war, it had become one of the unsung heroes of the Allied victory. Then suddenly it was over. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. The United States military now owned roughly 170,000 Quonset huts scattered across 6 continents and had no idea what to do with them. The original plan assumed these were temporary wartime expediencies that would be scrapped or abandoned once permanent facilities were built. But something unexpected happened. Nobody wanted to get rid of them. Commanders at bases slated for closure looked at their Quonsets and saw not obsolete relics but perfectly functional, maintenance-free buildings that could be repurposed for anything. The War Assets Administration, tasked with liquidating surplus military property, found itself with an unusual problem. There was more demand for used Quonset huts than they had inventory to sell. Veterans were returning home to a housing shortage so severe that families were living in converted chicken coops and sharing apartments with 3 other families. The construction industry, starved of materials and labor for 4 years, couldn't build fast enough to meet the demand. Into this crisis stepped the Quonset hut. Available for civilian purchase at liquidation prices, anywhere from $1,000 to $2,500 for a complete structure that would have cost $8,000 to build conventionally, if you could even find a contractor. The federal government encouraged this repurposing, prioritizing veterans for Quonset purchases. By late 1946, suburban developments made entirely of Quonsets sprang up around every major city. Roger Young Village in Los Angeles housed 750 families in converted huts. Vetville developments appeared near universities, where the GI Bill was flooding campuses with students who needed immediate, affordable housing. The architectural adaptation was creative and swift. Families added wooden facades to the curved ends, making the structures look less militaristic and more like quirky cottages. Interior walls divided the open space into bedrooms, living areas, and kitchens. Windows were cut into the steel sides, violating the original structural principles but making the spaces livable for family life. Some owners went further, burying the huts halfway into the ground for earth-sheltered insulation or connecting multiple huts end to end to create sprawling compound homes. Housing inspectors initially balked, but the housing crisis was so desperate that municipalities reluctantly granted permits. In Portland, Oregon, an entire neighborhood called Fairview Addition consisted of 350 Quonset homes. Residents planted gardens, painted their steel walls cheerful colors, and built porches that disguised the hut's utilitarian origins. Churches discovered that Quonset huts solved a different problem. providing worship space for exploding suburban populations without the decade-long capital campaigns that traditional church buildings required. The First Presbyterian Church of Levittown, Pennsylvania, held services in a Quonset hut from 1952 until 1967, when they finally raised funds for a conventional sanctuary. Dozens of congregations made the same calculation. $2,500 for immediate space beat $150,000 for eventual grandeur. The acoustics were terrible, the aesthetics underwhelming, but people could gather for worship next month instead of next decade. Some of these temporary church huts remained in service for 30 years, outlasting the generations who first considered them stopgap solutions. The education sector saw similar adoption. Post-war school enrollment exploded with the baby boom, and school districts faced the same impossible math that had plagued the military in 1942. They needed classrooms immediately. Conventionally built schools took years. Rural districts in particular embraced Quonset classrooms. A single hut provided space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States included at least one Quonset hut classroom. Some students spent their entire elementary education in these steel tunnels, learning multiplication tables and history lessons under curved ceilings that had once sheltered B-29 crews in the Pacific. The commercial and agricultural sectors joined the party. Small businesses, machine shops, auto repair garages, warehouses, recognized that Quonsets delivered clear span space without internal support columns, making them perfect for industrial work. A welder could set up shop in a surplus hut for less than 2 months' rent in conventional commercial space. The original Strand Steel Corporation, having helped design the military Quonsets, returned to manufacturing civilian versions specifically marketed to farmers. Thousands of Midwestern farms added Quonset storage buildings for grain, equipment, and livestock. The maintenance was minimal. Hose off the exterior once a year, check the bolts occasionally, and the structure would last indefinitely. This civilian adoption created an accidental architectural legacy. Quonset huts became embedded in American visual culture as symbols of practicality over pretense, function over form, and can-do ingenuity. They appeared in movies, television shows, and photographs as shorthand for post-war optimism mixed with austerity. Architectural historians initially dismissed them as temporary eyesores, but by the 1990s, preservationists began recognizing surviving Quonsets as important examples of adaptive reuse and vernacular architecture. Several achieved historic landmark status, protected as representing a unique moment when military technology successfully transitioned to civilian life. The story of the Quonset hut, however, did not end in the 1950s. Its DNA keeps reappearing wherever rapid, resilient shelter is needed. The 2010 Haiti earthquake that destroyed Port-au-Prince presented relief organizations with the same equation American planners faced in 1942. Immediate shelter for hundreds of thousands, no infrastructure, no time for conventional construction. The solutions that emerged, even if the designers didn't realize it, borrowed directly from Quonset principles. Arched frames, corrugated panels, prefabricated components that ship flat and assemble quickly. The United Nations High Commissioner for Refugees now uses shelter systems called RHUs, refugee housing units, that are essentially Quonset huts with 80 years of material science improvements. They use insulated composite panels and snap-fit connections, but the core concept is identical. A curved profile for strength and wind resistance, a self-supporting arch flat-pack shipping, and assembly by unskilled labor. A 2-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 Quonset specification. These units currently house over 200,000 displaced persons across the globe. Hurricane-resistant construction has also rediscovered arch geometry. After Hurricane Katrina in 2005, engineers found that curved structures consistently outperformed rectangular ones. Entire neighborhoods were reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact. This triggered research into aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength. The result looks remarkably like a Quonset hut because the physics haven't changed. The modern tiny house movement unknowingly reinvents Quonset principles when Designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using corrugated metal and self-supporting curves, selling to buyers seeking affordable, disaster-resilient, or off-grid homes. Some high-end architectural firms have even rehabilitated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes, transforming the utilitarian arch into a design statement. Military applications never stopped. The U.S. Armed Forces still deploy arch-style shelters in Afghanistan, Iraq, and other conflict zones. Current specifications call for units that can be helicopter-lifted, assembled in combat conditions, and survive IED blast waves. The materials have evolved to aluminum alloys and Kevlar-reinforced panels, but the design philosophy is instantly recognizable to the 1942 Quonset Point team. The most recent innovation is expandable versions that deploy from shipping containers, unfolding like origami into rigid arch structures within an hour. The economic argument that justified Quonset huts in 1942 remains compelling. When disaster strikes or rapid deployment is required, conventional construction cannot compete on speed or cost. A modern engineered arch shelter delivers weather protection for about $50 per square foot, including shipping and assembly. Conventional construction in the same remote locations can cost $150 to $300 per square foot and requires months instead of days. For humanitarian organizations and military logistics, this differential is everything. Perhaps the ultimate validation of the Quonset hut's brilliant design comes from the final frontier. NASA and private space companies designing habitats for Mars keep arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist severe dust storms, prefabricated components that ship on spacecraft, and self-supporting structures that require minimal foundation work. In the Martian regolith, the constraints of interplanetary construction, extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials, mirror the Pacific theater challenges of 1942 so precisely that engineers independently rediscover the same architectural solutions. When humans finally build permanent shelters on another planet, there is a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and a simple, brilliant curve.